Our next speaker, Kathryn Moeller, is Senior Associate Dean for the Natural Sciences and Professor at Stanford University, Sloan and Packard Fellowships, Fellow of the American Physical Society, the LePage Prize and Lectureship, and she will talk to us on the topic of currents and phases in quantum rings.
It's really an honor to be here, and I'd like to start by thanking Professor Halpern and the organizing committee for inviting me, and the Kavli Foundation for sponsoring this symposium. I think we're all aware that it's especially important to have private support, foundational support for science in the current era. I'd like to start by showing a picture of a vortex, which is something that we heard a lot about in the previous talk. This particular vortex is not a quantum vortex, but is a classical vortex. You know, I'm kind of amazed by how many people are still here, actually. All week, my friends have been coming up to me and saying, there's going to be a lot of people at your talk. And I've been saying, no, not nearly as many as there will be at the two talks right before mine. So I'd really like to thank you all for staying here and hearing all the talks in the session. Anyway, this is a picture of a vortex. It's not a quantum vortex. It's a classical vortex. It's a picture that was taken with a satellite. Satellites are very good tools for observing what happens in the fluid around the surface of the Earth. And it's particularly nice to do optical imaging because photons move more or less in straight lines at these length scales. And so you can get a really high resolution image of a classical vortex with a satellite that's relatively far away from it. But now imagine that instead of having a classical vortex that's 100 miles in scale, imagine that you have a vortex in a charged quantum superfluid that's sort of 100 nanometers in scale. How would it be different? Well, first of all, if it were in a charged fluid, then the charges that were circulating would create a magnetic field. And so you'd be able to see a magnetic field associated with this object. Second of all, if it were in a quantum superfluid, as Professor Kostelis just explained beautifully, then you would need the phase of the superfluid to be single-valued modulo 2 pi. And that means that all the vortices would be integral multiples of 2 pi. So if all of them were the smallest possible vortices, they would all look exactly alike. So this is an image of 3 vortices imaged with a magnetic probe above the surface of a superconductor, which happens to be yttrium barium copper oxide. And indeed, you can see 3 pools of charge. These all carry flux h over 2e, and they all carry the same flux. Studying vortices like these has been really useful in studies of superconductors. There are other talks that explain some of the details of some of these experiments. But in looking at vortices in many different superconducting systems over the years, both we and other groups have been able to test a lot of ideas and make a lot of observations about what is the nature of the superconducting state, what's the nature of the underlying quantum state in which these vortices live. So I'm not going to spend a lot of time talking about that today because when I gave a practice talk last week, my colleague Steve Kibelson urged me to make my talk more simple, and so I compressed the entire first half of my practice talk into just this slide. But I want to point out that there were talks earlier this week by my students Chris Watson and Hilary Noed saying more about what you can learn by doing imaging of 2-dimensional and 3-dimensional superconductors. What I want to talk about today is I want to talk about the analog of this effect in 1 dimension. So I want to talk about what happens in rings, because if you want to have something where you're manipulating the phase and want the phase to be single-valued, and you want to study a 1-dimensional object, you probably want to make it a ring. Or if you want to study a 0-dimensional object, maybe you want to put it inside a ring. So the title of my talk today is Currents and Phases in Quantum Rings. Let me start by explaining how the current and the phase are reminding you, for most of you, how the current and the phase are related. And I'll start with this picture from the famous paper by Aharonov and Bohm. Of course, the point of this picture was that the electromagnetic potential, the point of this paper was that the electromagnetic potentials operate on the particles even when the electromagnetic fields are not present at the same location as the location of the particles. But it's still a really good picture for illustrating fundamentally how phase and flux and currents are all related. So imagine that you have an electron beam, or more properly, don't think of an electron beam, just think of any charged particles. We don't even know what the particles are. And think of them as being not in a beam, but thinking of them as being in an incoming wave, either a single particle that's one wave, or if it's a wave of many particles, the particles should all have the same phase. They should all be coherent with each other. So imagine that they come in, and then you have something that splits them, and you have a left-going branch and a right-going branch, and then the wave or the particle comes back together in some interference region, and then you get either constructive or destructive interference depending on what relative phases the two arms have picked up. So you have the left-going particles and the right-going particles, and then they interfere. So the important point for our purposes is that if these particles are charged, for example, electrons having charge E, then their Hamiltonian will look like this. And the key feature of the Hamiltonian is the close relationship between the gradient and the presence of the magnetic vector potential. So what that means is that if you use a solenoid in the center of this region to apply magnetic flux, then when the two branches come back together, they'll acquire a relevant phase of the charge times the applied flux divided by h bar. And that gives rise to the definition of the flux quantum, which for carriers of charge E is h over E, 41.4 Gauss micron squared. And if you have something that has charge 2E, for example, Cooper pairs, it would be half of that. So the vortices that I showed you on the first slide, for the most part, carried flux h over 2E, except when they didn't. And of course, when they don't carry flux h over 2E, that's probably something very interesting that's going on. OK, so now suppose that you don't have a beam with two arms like this, but instead you have a standing ring, again, with a tunable magnetic flux through the center of the ring. What happens is that for the stable states in the ring, the phase has to wind by 2 pi. And because the phase has to wind by 2 pi times some integer, that means that the free energy will vary with the flux through the ring in a periodic fashion. And that means that there will be a persistent current that's periodic in the flux through the ring. And that period, again, could be h over E, or it could be h over 2E, or it could be something else. And whatever that period is will probably be very interesting. This is a really, really great way to probe phase-coherent quantum states. And it's not just the periodicity of the persistent current that tells you about the states, but also the magnitude of the current and how the magnitude of the current depends on all kinds of features, how it depends on temperature, magnetic field, beyond the flux quantum dependence, how it depends on disorder, how it depends on microwaves in your system, all the different things that it can depend on. Before I go on, I just want to point out that some of you will recall that you can also have very long-lived currents in classical states. If you have a classical ring with a very low resistance, you can have eddy currents that last for a very long time. And I want to point out, this is actually a popular PhD thesis question for some reason. I want to point out that that's a very different kind of situation. Those are not the ground state. The kind of persistent currents that I'm talking about here and that other people who study these phenomena talk about, it's really the ground state of the system to have a current flowing, even if the system has a finite resistance in the ring. OK, so imagine that you have some ring and you want to study its current. For concreteness, you can imagine a gold ring. I'll show you gold rings in a few minutes, and I'll also show you aluminum rings. So obviously, this is some mesoscopic ring. You're trying to get at its quantum mechanical properties. You can't just open up the ring and put an ammeter inside the ring. It would be great if you could, but the ammeter would likely destroy whatever state you're trying to look at. So what you want to do is you want to look at the currents in the ring in a way that doesn't disturb or bother the currents in the ring or require you to break the ring. And so what we do is we use a scanning SQUID device that has both a pickup loop and a field coil. And our current generation of SQUIDs were designed by John Kirtley and fabricated with a lot of hard work by Gerald Gibson at IBM and his team. So the essential part here is a pickup loop. And we're going to measure the flux through that pickup loop. And that pickup loop is hooked up to a SQUID that's quite a bit more complicated than obviously the pickup loop that I'm showing you here. Actually, maybe I'll just mention that it's kind of moving for me that IBM spent a lot of time in the 70s and 80s trying to make a Josephson supercomputer. A lot of people put a lot of work into that project. And as we all know, the Josephson supercomputer never became mainstream. Silicon just went screaming past Josephson superconducting technology. But I find it kind of beautiful that the fact that they put all that work into that at that time is one of the reasons why there are so many experts in superconducting electronics now that let my group make the devices that we need to study the quantum materials that might enable the next generation of exciting information process, as well as enabling the work of a lot of other groups as well. OK, so back to our experiment. We have this ring. And what we do is we put a current through our field coil. So here's our field coil. We put a current through our field coil, and then we put a current through that field coil that couples a flux into the ring, and it also couples a flux into the pickup loop. We have an astatically wound pickup loop field coil pair somewhere else in the design that cancels most of the flux that's coupled into the pickup loop from the field coil. But the field coil puts a flux through the ring, and that causes a current to flow in the ring, and that creates a little bit of extra flux in the pickup loop. So by measuring the flux in the pickup loop as a function of the current in the field coil, we learn what the current in the ring is as a function of the flux through the ring. So in order to make these measurements, we take this SQUID, and we actually we like to try to make, or to ask our collaborators to make, a lot of rings on a single substrate. And you might ask, why do we go to all this trouble to build a scanning SQUID? Why don't we just do what many other groups do? And if we want to make these kinds of measurements, try to fabricate our SQUID on the same substrate as our sample. And there's 3 reasons why we don't do that. The first reason is we really like to be able to study arrays. So it's really nice to be able to measure many samples in a single cool down. We find that to be a really big advantage to be able to get systematic dependence on various parameters and to check nominally identical rings and see how similar they are. The second reason is that it's really helpful to be able to check the background in the same cool down. So here we can go over a ring, measure that ring, move away from it, check the background, and then go and measure another ring. And the third reason, and possibly the most important reason, is that it's really nice to be able to study rings that are fabricated on whatever substrate is most appropriate for fabricating the ring on, and to not have that fabrication, because it's hard enough already if you're studying a new material, to not have that restricted by the fabrication that we can do, that we need to do for the SQUIDs. Okay, so that's our measurement technique. And let me give you examples of normal metal rings and conventional superconducting rings and what they look like with this technique. First of all, with normal metal rings, by normal metal rings, I mean rings where the mean free path is much smaller than the ring's circumference, and they have a finite resistance. So as I said earlier, naively, you might not think that they have a persistent current flowing in them. So, but they do have a persistent current flowing in them. However, the sign of the persistent current, as well as its magnitude, is determined by the individual disorder realization in a particular ring. So it could be either positive, it could be either negative. On average, it's pretty close to 0. But there's a distribution of these amplitudes whose typical sign is that of 1 electron circling the ring at the Fermi velocity, reduced by the ratio of the mean free path to the circumference of the ring. So there were some experiments by Chandrasekhar and Webb that were really quite beautiful experiments, if you've ever had a chance to see that paper, making similar measurements with a ring and a SQUID co-fabricated with each other. And they found that the persistent current was 100 times or so larger than this theoretical prediction in the 3 rings that they studied. And we wanted to figure out what was going on, so we built a scanning SQUID and started looking at rings. We didn't see any current. My student, Hendrik Bloom, worked really hard on improving the background and improving the noise. Still no current, kept working on it. He said, Cam, if I knew this experiment was going to be so hard, I would never have agreed to start this project. So I said, just try one more level. So he eventually reduced the background, the noise and background down to the point where he could see the original theoretical prediction. And at that point, we were able to see in a set of 15 nominally identical rings, each of them 1 1/3 microns, we were able to see that the persistent current is just dead on the theoretical, the naive, relatively naive theoretical predictions. I shouldn't have said naive, right? You guys are recording this. It's a beautiful theory paper. I just mean that it doesn't include any of the complexities that later theorists introduced to try to explain the discrepancy with the original theory. Okay, so the main point is that the observed typical magnitude agrees with the theory, and also I should mention that there were experiments by Jack Harris's group at Yale that also, around the same time using a different technique, that also agreed with the theory. And so we're all still, sort of very curious about what the discrepancy is between the different experiments. Okay, let me quickly tell you about mesoscopic superconducting rings, and then I'll move to talk about junctions. So imagine that you have a mesoscopic superconducting ring. If you take it at low temperature, temperatures that are small compared to the critical temperature, initially it just completely shields any applied magnetic field. And then as you increase the temperature and lower the barrier to flux entry, you see flux quanta start to jump into the ring. Until finally, when you get very close to the critical temperature, you see that flux quanta just freely enter the ring. And in fact, in order to get the shape of this curve right, you have to include fluctuations. You have to include fluxoid fluctuations. So when you start to include fluxoid fluctuations, you realize there are 2 interesting effects that both come into play. One is fluctuations, and the other is the little Parkes effect. So just to remind you, the little Parks effect, this is a plot of temperature versus applied flux, showing a superconducting region with an oscillatory behavior of the critical temperature. And the reason why that happens is that as you apply a magnetic field to a small cylinder or to a small ring, what you see is that when you start to put magnetic field in, the ring will flow current, and that current will cost some energy, and that will compete with the condensation energy and thereby lower the critical temperature of the ring. And this effect is most pronounced at half of a flux quantum. So you can imagine that if you took a sweep straight through this line here, very close to the critical temperature, you would see a superconductor, normal metal transition over and over again as a function of the applied flux. So when we measure the current in rings that are very close to the critical temperature, what we find is that there's a parameter that controls the strength of the fluctuations. And just to say that if I had more time to talk about this parameter, it would have the thallus energy in it. So I want to make sure that thallus was mentioned in all of the first 3 talks. But the point here is that there's some parameter that indicates how strong the fluctuations are. So when that parameter is small, if you look at this, you see that mean field theory and a theory that includes fluctuations and the data all agree with each other pretty well and show this flat region with no current flowing right around when you have an applied flux of half of a flux quantum. However, as you increase the importance of fluctuations, you find that you enter a regime where you can see both a little Parks effect and a fluctuation effect, and then a regime where really fluctuations basically swamp out the little Parks effect. And what the blue line here is data, and the red line is a theory by von Oppen and Riedel that includes fluctuations. So the combination of fluctuations and little Parks theory really beautifully describe the data in this ring. Okay, so let me move to talking about Josephson junctions and talk about measuring current phase relations in Josephson junctions. I hope I've convinced you that we can use scanning SQUIDs to very well measure the current versus the flux in a ring. So now imagine that you have a Josephson junction. First consider a superconductor, insulator, superconductor Josephson junction, and you have a phase on the left and a phase on the right. And as a function of this phase difference, a current flows in the ring, which has a sinusoidal current phase relation. So the current is some critical current times the sine of the phase. However, you don't have to make your junctions with an insulator in the middle. You can make them with anything in the middle. Another superconductor, a ferromagnet, a semiconductor, a topological material. Then you would call them SFS junctions or SS prime S junctions or SNS junctions. And then the current phase relation could be something else. Not a sine wave. It still has to be single valued modulo 2 pi, but it could have a very interesting functional form. And there's been a lot of work for decades on determining what those functional forms are and figuring out better ways to measure them. So by now, you know how we're going to measure them. We're going to take this junction, we're going to put it in a ring, and then we're going to use the pickup loop and field coil of our SQUID in order to measure those rings. So I could talk about various different kinds of junctions, but what I want to do here is I want to give you a sense of, in the effort to implement the topological theories that we heard about in the first 2 talks, what are some of the real materials issues? What are some of the measurement techniques that people use, and what are some of the real materials issues that come up? So let me talk specifically about our most recent experiments, which are presently under review, looking at junctions that are prime candidates to realize these kinds of effects. So there's a thing called Majorana modes, which Professor Haldane kindly introduced in the first talk. In 1937, Majorana proposed a particle that's its own antiparticle, and there have been many schemes proposed to engineer Majorana-like bound states in superconductors, and these states could be useful for topological quantum computation. Unfortunately, a lot of that has been covered and will be covered in other talks in this conference, so I'm not going to go into the details of that. A lot of these experimental proposals are based on a paper by Kitaev in 2000, and so let me just briefly describe that one. It wasn't actually a specific material suggestion, but was more of a toy model schematic of what kind of material systems people might look for. So in that case, you have 2 conventional superconducting leads separated by a wire, and you somehow engineer a spinless p-wave superconductor into that wire. And when you do that, you have a topological superconductor in the wire and 2 trivial or non-topological superconductors in the leads, and then at the edges of the wire, you end up with a boundary mode of the sort that Professor Haldane described. there's been a lot of work on trying to fabricate and characterize these systems, and you can hear about it. In fact, there's a parallel session on Majoranas right now where you can hear about a lot of the work that experimentalists are doing in fabricating these systems and also trying to realize, trying to conclusively demonstrate the existence of Majoranas in them. When you look at the theoretical papers on this subject, the theoretical papers over and over again mention the importance of current phase relations in trying to characterize topological junctions. And so I won't read all these quotes, but I'll just leave them up for a minute so that you can run your eyes over them and see how people talk about the Josephson current, the current phase relation, the critical Majorana-Josephson currents, the measurement of the supercurrent through the junction, and the Josephson current flowing across the junction allows the deduction of the presence or absence of this extra quasi-particle. So this is highly motivating for measuring current phase relations. And what I want to do with my last few minutes is try to explain to you a sense of how the current phase relation can tell you something about the modes of whatever it is that you're coupling the two superconductors through. Okay, so when you have a junction, the current in a junction is carried by Andreev bound states that are also called modes. So this is a sketch that kind of mixes spatial dimensions and energy dimensions. But imagine you have two superconducting leads. And of course, you can have direct tunneling of Cooper pairs between the leads. But if the medium between the leads allows you to have particles, that direct tunneling can easily be swamped by this process called Andreev bound states. So imagine that you get a quasi-particle traveling across the junction. The quasi-particle hits one of the leads, and then it's reflected by a process called Andreev reflection, which allows a Cooper pair to enter the other lead and sends a hole back the other way. So that's the visual description of the process. If you write down the relevant equations that describe these three regions of space, you find that there's a spectrum of Andreev bound states in the junction. And this is an example of the spectrum of Andreev bound states. This is just one Andreev bound state, or more properly, it's a pair of electron-like Andreev bound states and another doubly degenerate pair of hole-like Andreev bound states. And their energy is changed by the phase difference across the leads. Now, these two states, when they reach pi, have an avoided level crossing, and so the actual spectrum ends up looking like this. And then the current is the derivative of the energy with respect to phase, and so the current of these two branches ends up looking like the red curve and like the blue curve. This figure actually shows one of the key most features of high transmission few mode junctions, which is that if you have high transmission, you have a highly skewed current phase relation. And just to show you a plot from a lovely paper by Bienecker called 3 Universal Mesoscopic Josephson Effects, if you look at the current phase relation, you can see the dotted line is for a tunnel junction, the dashed line is for a disordered point contact, and the solid line is for a single mode that has perfect transmission. And I also here want to mention the Quantronics group in France, which has done quite a lot of work, as have other groups, of trying to characterize these transmissions by various means. Let's see, before I leave this slide, I should also mention that when you have multiple Andreev bound states, the current that you carry is determined by a sum over the different Andreev bound states. So now, let's suppose we want to hunt for Majoranas. This is a figure from Kitaev's paper that shows that this level crossing, which is an avoided level crossing in a trivial superconductor, can become a level crossing that's protected by fermion parity in a topological superconductor. And so that means that the typical or trivial Andreev bound state leads to a current phase, it leads to an energy versus phase relation like this one, whereas a topological junction, or one that has a Majorana bound state in it, leads to an energy phase relation like this one. And that leads to two very different current phase relations. One of the current phase relations is highly skewed and 2-pi periodic, but as soon as you tune into the existence of a topological junction, you should get a current phase relation that, although it's 2-pi periodic, as it's required to be, will appear to be 4-pi periodic if you can measure it fast enough. So what you want to look for in direct measurements of the current phase relation are something that's tunable, has a small number of modes, has high transmission, and ultimately something that you can tune into a state of 4-pi periodicity. The measurements that we're making are made in, so I could talk about a number of different junctions in which it might be possible to realize these things. What I'd like to tell you about is our work on epitaxial aluminum indium arsenide nanowires grown by the group at Copenhagen. So they grow these nanowires, and then they etch aluminum out of the center of the nanowires to give us an indium arsenide region in the center. And theoretically, if you put an in-plane field along these nanowires, you should be able to tune this into a topological state if you can also tune carrier density. Then they evaporate leads on this for us and close the leads into a circular loop. And here's a sketch of such a loop with a finger to control, to ground it, and with a backgate, and then with the sketch of our pickup loop field coil pair imposed on top of the loop. And that little tiny gap there is where they put the nanowire. Okay, so we're measuring current phase relations in these junctions, and this is the current phase relation of 30 different junctions. And I've ordered these current phase relations in order from the least supercurrent to the most supercurrent. Let's pick one of these junctions and concentrate on what it looks like when you tune it versus gate. And when you tune it versus gate, you see that you actually have resonant peaks where as you change the gate, you go from having no or very small supercurrent to having quite a bit of supercurrent, back to having relatively no supercurrent. So let's concentrate on the data from this junction, and especially let's concentrate on the low gate voltage area. And the best way to characterize the skewness is to represent the current phase relation as a sum of Fourier components. And when you do that, the presence of a second harmonic is the best indicator of the skewness of the junction, although actually the relative ratio of all of the harmonics is not something that's completely free to vary. If this junction is described by the theory that I showed you a few slides ago, then the relative ratio of those harmonics will be well determined by that theory. So if we look at this junction's parameters as a function of voltage, we see that there's a substantial peak in the current at low gate voltage, and then we see a peak where there's quite a high degree of skewness. And if we take that current phase relation, here I'm showing you the data together with the theory, and it really agrees extremely well with the current phase relation that it's expected for a single transmitting mode with nearly perfect transmission. So if we're looking at what are the necessary features that we want to get as we move towards Majorana junctions, what we've done is we've shown that we can measure the current phase relation in a number of different junctions. We've shown that you can build devices that have a small and tunable number of modes with high transmission, and the transmission is also tunable. And our next steps in this are to look at many different candidate junctions that we could study and to tune into a 4-pi periodic regime. And I'll be happy to take questions about how we're going to do that. But first, I want to mention that the gold and aluminum ring measurements that I showed you were made by Hendrik Bloom and Nick Koschnick, that our indium arsenide devices were grown at Copenhagen, and the devices were also fabricated at Copenhagen. And I especially want to acknowledge Eric Spanton, who made the current phase relations on the indium arsenide nanowires that I just showed you, as well as Zheng Shui and Sean Hart, who are making the next generation current phase relationships now. Thank you for your attention.
Thank you very much, Professor Moller. Are there questions?
May I ask a trivial question? What happens with the Joule heat when you have persistent currents? You said it's a ground state, and yet at the same time, if there's a heat dissipation, that can't possibly be recorded with second law thermodynamics.
Yeah, so there won't be exactly a Joule heat because that's something that moves you towards the ground state. So once you're in the ground state, you're in the ground state, and then you won't dissipate more heat. Yeah, I don't think it's a trivial question at all. I think it's a very profound question. Yeah, and it's why it's initially surprising that you would have persistent currents in normal metal rings.
You mentioned that you'd be interested in going with the topological regime with the indium arsenide wires,
yeah,
which of course needs magnetic fields.
Yes.
Do you anticipate some technical challenges with this CPR sort of, with the SQUID loops and all of the stuff that goes into it in doing that?
Yes, there's a very strong technical challenge, which is that the SQUIDs don't work in magnetic field. So yeah, that's a big technical challenge. So the thing that we can do is we can push the magnetic field that the SQUIDs work in. We can explore other measurement technologies. This is a pretty good one, so that's challenging, but we're looking at other ones. We can also try to engineer the magnetic fields in a way that the magnetic fields are at the junction and not at the SQUID. And that seems like maybe plausible. And then also, of course, what you'd really like to do is if you're going to use these devices in the real world, you really would not like to have to put them in a large field. So it would be great if we could just solve the problem of how to get a ferromagnetic insulator epitaxially connected to the indium arsenide nanowire with very good exchange coupling. So that would be the ultimate idea, would be to solve that very, very difficult material science problem. Yeah, and then in the meantime, there's also other candidate materials to look for these things in that don't require such high field.
Thanks.
That's a quick overview of our plans.
You have a question? So a short one.
So I've noticed that the skewness inverts as a function of gate.
Oh,
Can you
yes.
comment on that?
Yes, absolutely. So actually, it gives me a chance to say that I really appreciated the referee process on this paper. And our referees were, two positive, one a little dubious. But the one who's dubious really pushed us, and if you're here, I want to thank you, really pushed us to talk about this. And that we'd kind of had some speculations, but that caused us to look deeply into the literature and do better modeling. And so we actually think that it's a pi junction that's related to the presence of a charging effect. And so we're writing that up now to further improve the paper. Yeah. And I'd be happy to talk more about that afterwards, too.
Again, thank you very much, Professor Moeller.
Yeah.